Yes, ma'am.
Okay, so look at the conductivity part here. We know lambda m is inversely proportional to C. As we keep on diluting, decrease the concentration, that means you're diluting it, the molar conductivity value keeps increasing. So, when is it maximum? When the C is at its minimum. What is minimum? When the concentration approaches zero. Concentration doesn't become zero. Concentration approaches zero. For example, I've got 1 mole of KCl and 1 liter of water. Okay, so can I say it is 1 m concentration, children?
Yes, ma'am.
Okay, if I'm going to add 1 more liter of water into this container, what will happen to the concentration? I'm going to add 1 more liter. Now what will happen? 1 mole of KCl is present in 2 liters of the solution. What will happen to the concentration?
Point 0.5 m.
zero point 0.5. Okay, let me add 2 more liters. Make it 4. What will happen to the concentration?
0.25.
0.25. I'm going to add one more lot of 4 liters. 8. 0.125. I'm going to add 8 more liters. Make it 16. 0.05. Yes, children? How much it
Yes,
will
ma'am.
be? 0.0. Divide and tell me quickly. 0.125 divided into half. How much it will be?
Point
0.65.
0.625.
0.065. 625. Okay. Then again, I'm going to add 16 more liters to make it 32 liters. What will happen? 0.0312, right? And so on. This continues. So, but the 1 mole remains 1 mole of KCl, na? The only difference is now it was present in 1 liter, now it is present in large volume of water. So can you say that the concentration has become zero
No,
even after diluting so much? Can you say that the concentration has become zero?
no, not exactly.
Not exactly. Even if you keep on adding water, let us bring 100 liters of water, 1000 liters of water, that 1 mole of KCl is still there. So the concentration of KCl never becomes zero, but it approaches zero. Can you accept that? It approaches zero. It's very
Yes,
small, so small that it is almost zero, but not zero. When it is infinitely diluted, when the concentration has been infinitely decreased, the lambda m value will be at its maximum. That value of the molar conductivity, when the concentration approaches zero, can be represented as lambda m naught or also is represented with infinity symbol on it. All the three are same. This value is its maximum possible value, and that value is called as limiting molar conductivity. I'm going to throw a stone up. Okay, I have a stone. I'm going to throw up. Okay, with all my strength. I applied little strength, it went up to this height. Little more strength, it went up to this height. Little more here. I apply maximum strength, whatever I can. Maybe the stone reaches around 50 meters height. That's the limit. I cannot throw beyond that. That's the maximum ability. When you have reached your maximum ability, I will say it is the limit, correct?
Yes, ma'am.
Same way, when the concentration has been infinitely diluted, when the concentration has been infinitely diluted, you keep adding water to the solution, the concentration will keep on decreasing, 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 decreasing. When the concentration has been infinitely decreased, dilution has been infinitely diluted, the lambda m will be the infinite value, maximum possible value. That maximum possible value is limiting value. Nothing more than that is possible. So we say it is limiting molar conductivity, and it is represented with lambda m, concentration approaching zero, or lambda m naught, or lambda m infinity. Any problem with this?
Ma'am, if the limiting value is infinity, then how is it limiting, ma'am?
No, it's not limiting value is not infinity. Okay. Graphically, we will understand. The value is a maximum possible value. See, I have a cow and I'm going to milk the cow.
Yes, ma'am.
Continuously, I'm going to milk. Is it going to give me infinite amount of milk?
No, ma'am.
No, a cow maybe at a time can give me around 5 liters. Just because I'm continuously milking, will it give infinite liters?
No, ma'am.
I'm milking the cow for probably 15 minutes and I'm getting around, say, 3 liters. I milk it for 15 more minutes. I get around 4 liters. Then poor cow will not yield to my force. So I'm continuously doing that, continuously milking it. So maximum it is able to give 5 liters. After 5 liters, what it can do? I can milk for 1 hour also, or 2 hours, or 10 hours also. Will the amount increase?
No, ma'am.
It has reached its maximum value. Understood? So is 5 liters infinite? No, na.
No, ma'am.
It has reached its maximum. The maximum does not mean infinite. Understood?
Yes, ma'am.
Yes,
Ah,
ma'am.
okay. Now, okay, that's a very good example, probably. I've used this explanation first time in all these years. Okay. Now look at the graph. Okay. Now let us see. The lambda m versus square root of c. We are going to plot a graph. Okay. This is as per an equation which is called as D by Huckel-Onsager equation. Lambda m at a given concentration is equal to lambda m at concentration approaching 0 minus a times square root of c. Okay. So people studied the effect of change in concentration on the molar conductivity, and they said that molar conductivity at a given concentration is equal to the limiting molar conductivity minus a times square root of c. So it is dependent on the concentration. So now we plot the molar conductivity at a given concentration versus the square root of c, thinking that this is y, this is x. So what should be the slope of, what should be the slope? Assume if it is a line. I'm trying to put it in y is equal to mx plus c. What should be the slope of this graph?
A, ma'am.
Minus a, na?
Minus yes.
Minus a. So the line is basically having a negative slope. Fine?
Yes,
Okay.
ma'am.
Okay. What is the intercept at the y-axis?
Lambda concentration will
Lambda
be
m,
0.
concentration approaching 0, or we can say lambda m naught, or we can say lambda m infinity. All the three terms refer to the same. So what do I have to do to get? I just have to extrapolate the line and see where it meets the y-axis and call that as lambda m infinity. What
Yes,
is
ma'am.
the concentration when I'm measuring the lambda m infinity according to the x-axis?
0. Almost
So,
approaching to 0.
is it possible for you to make a solution of KCl or any electrolyte with 0 KCl in it? No.
No, ma'am.
So it's a theoretical value. We keep decreasing the concentration from a higher value, lower value, lower value, lower value, lower value, lower value. But I cannot reach 0. If I reach 0 concentration, that means there is no KCl in it. So we can do the experimentation over some range of concentration, from a high concentration value to a low concentration value. Since we get a straight line or roughly a straight line, I can always do extrapolation work and call the intercept at the y-axis as lambda m infinity. Is that clear?
Yes.
Yes, ma'am.
Okay. Now, this kind of a graph is obtained for something like a strong electrolyte, like KCl, NaCl. You get a straight line for a strong electrolyte. Okay. A straight line is influenced by fewer factors. Okay. Assume that, okay, you are going on a tour. Okay. And you are asking money from your father to go for the tour. The money that you have is directly proportional to what your dad can give, correct?
Yes, ma'am.
It is linearly proportional. Okay. Another family tour. This fellow is going to the tour. The money with him comes from dad, mom, grandmother, grandfather. What will happen? And aunt, uncle, and so on. What will happen to the money?
It will increase a lot, ma'am.
It will shoot up. The money will shoot up, right? Because the amount of money that you have is not contributed by a single person whose behavior is learnt by you. It's contributed by so many, correct?
Yes, ma'am.
So it will shoot up. The money with you will shoot up like this. When you look at a weak electrolyte, not just simple parameters, but 2 or 3 complex parameters come in. So for a strong electrolyte, the graph looks like this. Okay, it's very important to study why the graph for a weak electrolyte like CH3COOH looks like this, and for KCl it looks like this. Shall we start?
Yes, ma'am.
Okay, when it is KCl, we are measuring the lambda m at a given concentration. When it is KCl, almost at all concentration, it is infinitely diluted. It's fully dissociated. It's like the dad. He can offer you 2000 rupees, that's it. And if you keep milking him, what will he do? How much more he will give? He has fixed in his mind, I am going to give 2000. How much more can you extract from your dad?
Nothing, ma'am.
Maybe 100 more, that's all, correct?
Yes.
Because he knows the cost of the tour. More money, more trouble. Okay. Sometimes money leads to trouble when you are not so responsible. Okay. So already your father gave 2000 rupees. So already he gave 2000. And if you keep pressing, he gives some more. So with the increase in the pressure, he gives some more, little more. 2000 becomes 2100. But think about the other fellow, CH3COOH. See, in the case of KCl, at all concentration, be it higher concentration or lower concentration, it was 100% dissociated. Here also 100% dissociated. So what is the point in diluting? What advantage do you get on diluting?
To reduce interionic
That's all.
forces.
That's all. That is the advantage. So it's giving 100% already. By diluting, you are getting weakened intra-ionic forces. So it contributes to some more. So the value increases by a small value. The molar conductivity value increases by a small parameter for a strong electrolyte like KCl because it was already 100% dissociated at higher concentration. The degree of dissociation is not going to improve any further. It's like your dad, he gave what you should get, 2000. If you keep asking, he will hand over 100 more to you. That's all. But think about weak electrolyte. They are saying you don't go to the tour at all. So initially zero money. Then suddenly, okay, permission is granted. Then people start pouring in money. So initially the molar conductivity value is very small because it's a weak electrolyte and it does not dissociate. There is something called as Ostwald's dilution law. Here, there is no mention of that. But what it is. It's a simple law. What it says is, Ostwald dilution law says that for a weak electrolyte, the degree of dissociation increases with dilution. So at higher concentration, the degree of dissociation was very less. It was probably 5% dissociated. But when you decrease the concentration, when you are going to decrease the concentration, it reaches greater degree of dissociation. So when you decrease the concentration, probably the degree of dissociation has increased to 60%. Not only that, it also is helped by the dilution factor. So there are two things contributing, no? One, you are getting more ions. Number two, those ions are in diluted state. They will freely move. Whereas in case of KCl, it was 100% dissociated at a greater concentration. Any decrease in the concentration will only add to the dilution factor. You are not getting any. There are the two factors. Number one, the degree of dissociation or availability of ions. I'll put it as availability of ions. Number two is their mobility. When you talk about the KCl, this is not going to increase on dilution because it was always 100%. Any dilution increases only the mobility. But when it comes to CH3COOH, availability of ions increases on dilution and they become more mobile. Two factors contribute, like grandfather, grandmother join to give you money. What will happen? It shoots up. Is that clear?
Yes.
Yes, ma'am.
Yes.
Yes, Pranav?
Yes, ma'am.
Okay. So now tell me, can you extrapolate the line for this weak electrolyte and find out the limiting molar conductivity of CH3COH?
Infinity, ma'am.
Where it will meet the y-axis, God only knows. But where the line of KCl will meet the y-axis, yes, we know. Why? Because the behavior is very smooth. It's linear behavior. So we are able to extrapolate the line and see that, oh, it meets here. So that becomes the limiting molar conductivity of the KCl. So limiting molar conductivity of a strong electrolyte can be found. There was a question once. How do you find out the limiting molar conductivity for a strong electrolyte and for a weak electrolyte? For a strong electrolyte, we plot the lambda MC versus square root of lambda MC versus square root of C, extrapolate the line, extrapolate the graph, and intercept at the y-axis. Intercept at y-axis is the lambda m infinity. Are we able to understand this? How do we determine the
Yes.
lambda m infinity for a strong electrolyte? By plotting lambda mc versus square root of c and extrapolating the graph, searching for where it intercepts at the y-axis. The intercept at the y-axis becomes lambda m infinity. Are we clear?
Yes, ma'am.
Yes.
Okay. But for a weak electrolyte, it is possible where it meets the y-axis?
No, ma'am.
No. So what we do is we are going to find out the lambda m infinity or lambda m naught for a weak electrolyte by indirect way. Okay, indirect way. Now, what is that indirect way? The indirect way is to apply something called as Kohlrausch's law. There is something called as Kohlrausch law. What does this Kohlrausch law say? Okay, supposing Ishan, okay, is with X. Ishan's behavior is something. Ishan is with Y. Will Ishan change his behavior?
No, ma'am. Yes, ma'am. Yes, ma'am. Yes,
Okay.
ma'am.
You will change. Okay.
Depending on the process.
Maybe, you sometimes know you will have to nod your head. Yeah, I also like ice cream. I also like this movie. I also like that person. Okay. If you are with Z, will your behavior change? Obviously, If it was different from X to Y, Y to Z also, it will change, right? So when Ishan is with X, some behavior. Ishan is with Y, some behavior. Ishan is with Z, some different behavior. But ions are not like that. Supposing I am measuring what Na plus, how much charge can Na plus transport? How much current can Na plus transport? Because when you are talking about a solution, ions only are the charge carriers, na?
Yes, ma'am.
So now I am thinking of finding out how much sodium ion can carry the charge. So let us think of sodium is with chloride, sodium is with bromide, sodium is with sulfate, sodium is with nitrate. And I am talking about sodium ions behavior at infinite dilution. Or when it is infinitely diluted, it is infinitely away from the anions, no? So is it going to be different with chloride, different with bromide, different with sulfate, different with nitrate?
No, ma'am.
When it is concentrated solution, yes, it will be affected. But when it is infinitely diluted, sodium ion is free from interionic attraction from chloride. Sodium ion's behavior is independent of bromide, independent of sulfate, independent of nitrate. So whether you find out the sodium ion's conductivity value by using NaCl, NaBr, Na2SO4 or NaNO3, the ion's conduction ability remains the same, not like Ishan. Understood?
Yes, ma'am.
And the main reason why it remains same is we are infinitely diluting, no? Understood? So this helps us to actually get the molar conductivity, limiting ionic conductivity of the various ions. Okay, I'm just going to show you the values. If it is here. And it is independent of what it is paired up with. See, the H plus can contribute this much conduction ability. H pluses, look at the unit. Isn't it the unit of molar conductivity? 1 mole of hydrogen ions can show this much of molar conductivity. Now, whether H plus is with Cl, H plus is with Br, H plus is with I, or H plus is with CH3COO, doesn't matter. Understood? So, the limiting molar conductivity of the ions is independent of its anion, its counterpart. Similarly, the limiting molar conductivity of hydroxide is independent of the cation. Whatever be this, it is sodium hydroxide, this much only. Hydroxide in sodium hydroxide, this much. Hydroxide in potassium hydroxide, this much. Hydroxide in calcium hydroxide, only this much. 199.1 Siemens centimeter square per mole. Why it is independent? Because you have infinitely diluted. You have separated the anion from the cation by infinite distance, theoretically. Cation is independent. Doesn't matter what anion it was with. Anion is independent of the cations. Are we getting the point, children?
Yes, ma'am.
So supposing I want the molar conductivity value at infinite dilution for calcium chloride. Can you use the table and tell me how much it will be?
119 plus 76.3.
2 times 76.3. Because there are 2 chlorides, no ma?
Yes, ma'am.
Understood? So calcium can be with anybody, but calcium's ability to conduct is so much. So if you want for calcium chloride, you just have to go to the table, pick the calcium chlorides and add the values. What if you want it for calcium sulfate? The limiting molar conductivity for calcium sulfate, what you will do?
119 plus 160.
160. That means this itself becomes the Kohlrausch's law. What is Kohlrausch's law? What is Kohlrausch's law? Kohlrausch's law of independent migration of ions states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and the cation of the electrolyte. Because these values are independent, unique. It's not going to be dependent on its surrounding. The acetate's contribution is irrespective of whether it was with H plus or whether it was with NH4 plus or whether it was with K plus or Ca2 plus. Understood? Understood?
Yes, ma'am.
Okay, go through this term and understand these. I'll just get back. Yes, ma. So lambda m of NaCl can be written as independent contribution of sodium ion summed up with independent contribution of chloride. Any problem with that?
Ma'am, how did they find the lambda m naught of CH3CO minus?
Okay, I'll tell you how. Okay. Say, for example, a very simple explanation. Ishan and X went to the coffee shop and they had, Ishan consumes only same amount. Okay. He buys snacks for same amount. Obviously, that's what is the concept now. The
Yes,
ion is going to offer same amount irrespective of his partner. Sodium ion contributes the same amount irrespective of its anion counterpart. So Ishan with X, okay, and the expenditure was 100. Now Ishan with Y,
okay.
the contribution becomes 120. X and Y went out and they spent around say 150. Can we not use these three equations to find out how much Ishan spent?
Yes, ma'am.
Assume Ishan is written as Q. So we'll say Q plus X is equal to 100. Q plus Y is equal to 120. Now X plus Y is equal to 150. So I've got 1, 2, and 3. 3 variables, 3 equations. Can I not find out individual contributions?
Yes, ma'am.
So that is how they are finding it out. So they might find out for NaCl. They might find it out for NaBr. Is it okay? Similarly, they may find
Yes,
it out for KCl, KBr, and a number of substances. Manipulate these values to get the contribution of individual ions. Got it?
ma'am, but CH3CO minus doesn't dissociate completely right now. It dissociates
That is a
depending
problem.
on.
That's a very good problem. It's a very, very good problem. Okay. So what do you do now? That's the question here. So supposing I want to find out lambda m of CH3COOH. Now, will I get the see, this is capital lambda and this is small lambda. This is all Greek letters. Alpha, beta, gamma, okay, your theta, rho, kappa, okay, and whatnot. You are using so many eta, then chi. Remember mole fraction chi, okay. All
Delta.
these are Greek alphabets. So in Greek, the lambda is this in small case. In capital case, this is lambda. So it's lambda. Got it?
Yes, ma'am.
Okay. So lambda m infinity will be definitely sum of CH3COO minus and contribution of H plus, correct?
Yes, ma'am.
But I know that this is not going to dissociate. But I can take something like CH3COONA, na? Isn't it a strong electrolyte?
Yes, ma'am.
Okay. So what will I do to get
Yes.
the lambda m for the CH3COH? What I'll do is I will add the ionic mobility of Na plus, ionic conductivity of chloride at infinite dilution, and subtract the lambda m of NaCl. Think about it. In fact, what I did is I added the molar conductivity of sodium chloride and subtracted the molar conductivity of sodium chloride. Any problem with that?
No, ma'am.
No. Okay, already this is the equation. To that equation, what I'm doing? I'm adding 10 rupees on this side and 10 rupees on this side. It remains balanced. I'll bring this 10 rupees and write it here as minus 10 rupees. Over. Still it is balanced only, no?
Yes, ma'am.
That is what we are doing here. So I'm adding NaCl and subtracting NaCl. But this NaCl, you can get the sodium ions mobility. You can combine these two, and you can say that it is molar conductivity of CH3COONA at infinite dilution plus molar conductivity of HCl minus molar conductivity of NaCl. Now, all these three are strong electrolytes. So, can their molar conductivity values not be obtained by extrapolation of the line on the graph?
Yes, ma'am.
This is a strong electrolyte, this is a strong electrolyte, this is also strong. But when you add all the three, are you not getting the limiting molar conductivity of a weak electrolyte?
Yes, ma'am.
This is the use of Kohlrausch's law. The Kohlrausch's law of independent ion migration says that molar conductivity of an electrolyte is the sum of the molar conductivity of the constituent ions, irrespective of their surrounding. So I'm going to make use of this fact and go for modification of, or we can say we are manipulating the values. So I'm going to add NaCl, subtract NaCl. NaCl, what I added, I can roughly take it as NaCH3CONA. H plus can be combined with HCl. This can be converted to strong electrolyte. This can be converted to strong. This is already a strong. For them, the values are obtained from the graph by extrapolating the lines. So you have got those values. When you add the three, you get your required weak electrolytes value. This becomes the answer for this question. How do you find out the limiting molar conductivity of a weak electrolyte? By using which law? By using Kohlrausch's law. Understood all this?
Yes, ma'am.
Yes, Pranav?
Yes, ma'am.
Okay. Now, I have not done this. Okay. Again, when you are defining the limiting molar conductivity, never say that the concentration is zero. When the concentration approaches zero, if this term is not there, zero. In the definition of limiting molar conductivity, if you say conductivity of an electrolytic solution whose concentration is zero, then that's all. the concentration approaches zero, the value is said to be limiting molar conductivity. Is it clear?
Yes, ma'am.
So for a strong electrolyte, we follow the D by Huckel-Onsager equation. The name is also not given. We follow the D by Huckel-Onsager equation, plot it, get a straight line, extrapolate and get the lambda m infinity. But for a weak electrolyte, the same graph does not give me a straight line. So we go and use the Kohlrausch's law to find out the limiting molar conductivity of a weak electrolyte. But why do we need the limiting molar conductivity? Why so adamant in finding out the limiting molar conductivity? You know why? In the class 11, did you not study the degree of dissociation of acetic acid is 1.74 into 10 to the power minus 5 and all? Did you not learn for weak
Yes,
electrolytes?
ma'am.
What is this actually? Degree of dissociation. Assume that in your class there are 40 students. On a particular rainy day, only 15 turned up. What is the degree of presence in your school?
15 by 5.
15 out of the 40 possible, right?
Yes, ma'am.
If everybody had come, it would have been 40. But today it is 15 out of 40. So alpha is lambda m at a given concentration by lambda m at infinite dilution. What did I say? An electrolyte is going to give its maximum possible value when it is infinitely diluted. Compared to that, at any different concentration, it is going to offer less conductivity only, no?
Yes,
The
ma'am.
ratio of lambda mc to lambda m infinity is alpha. So in 11th standard, whatever alpha values you studied for the various weak electrolytes are all estimated by only these kind of conductometric experiments. Did you understand why the lambda m infinity is required?
Yes, ma'am.
Hmm. Okay, now I'm going to give you a small work. Try to do it on your own. And later on, we will do this together. Okay. Okay. So I will ask you not to do these as per the textbook. If you already have done it, fine. So we'll learn it fresh. Okay. Don't look at the solution. Try to solve if possible. Okay. Don't look at the solution. Okay. Or the other choice will be look at the solution. If you are getting it, fine. If you are not getting it, get it from me in the next class. So example, these two examples. Okay. And one Kohlrausch's law sum. Do these questions today itself. 2.7, 2.8, 2.9. So I'm giving you 5 example questions. Go through them, understand, and come in the next class. Okay? Okay?
Yes.
Okay, ma'am.
Okay. And another thing is this for this week, and of course we have today's Wednesday. So at least this week, till now, no disturbance. I may probably cancel 1 or 2 classes. Okay, you were asking me, no? So we have holidays and all. I told you if I have to go somewhere, then if you are not there, I can record and send. But if I'm not there, no class, no. So that's why I did not give you formal holidays. So I may take leave. I don't know. If I'm available, I'll definitely take. If I'm not available, because Monday, probably I'm not available. Friday also, I need to see. Monday, I have to go to some place. I don't think so. I'll be able to come back. So next week classes, the next 4 classes, particularly in this month, no? Upcoming Friday, next Monday, Wednesday, Friday. If I'm available, I'll definitely take. If I'm not available, I'll send message. Clear?
Yes, ma'am.
Okay. Yeah. Okay. Yes, children.
Ma'am, doubt, ma'am.